There are nights when the sky changes in almost unbelievable ways. A star is still there during one observation, and then, the next time, it disappears entirely. No prolonged explosion. No spectacular display for watching telescopes. Just a sudden void, as if someone had flipped a cosmic switch. What remains is not the familiar remnants of a dead star. It is a strange region of space, where our intuitive rules about the universe become nearly useless. It is a place where gravity becomes so extreme that even light, traveling at about 186,000 miles per second, cannot escape. When a star ends its life this way, it does not merely change state like water freezing into ice. It leaves a permanent scar on the fabric of space-time itself. What makes this story staggering is that the process is not rare. Somewhere in the universe, right now, a star is collapsing in this way. All of it occurs in a few seconds. A mass that once spanned millions of miles is compressed to smaller than an atom. All that matter and energy is forced into a tiny space. So small that familiar physical equations start to fail. They return only infinite numbers before breaking down. We call this point a singularity simply because we truly do not know what happens there. But to understand that extreme moment, we must rewind time to before everything began collapsing. Imagine a star 20 times more massive than the Sun. For millions of years, it exists in a silent struggle with itself. At the core, nuclear reactions generate enormous pressure, pushing matter outward, while gravity attempts to pull everything back in. These opposing forces balance perfectly, and the star shines steadily, converting hydrogen into helium, then forging carbon and heavier elements, a colossal cosmic forge. But massive stars live fast. If the Sun can last about 10 billion years, a star 20 times its mass survives only about 10 million years. And when fuel in the core runs out, the balance maintained for millions of years disappears almost instantly. No pressure remains to counteract gravity. In less than a moment, the star's core begins to collapse. Matter that once stretched thousands of miles is compressed to just a few meters. The collapse happens so quickly that the outer layers do not even have time to realize what is happening at the center. When the core rebounds, a colossal shockwave blasts outward at thousands of miles per second. That is a supernova. In those brief seconds, the star shines brighter than an entire galaxy. The energy released in that instant exceeds the total energy the star ever produced in its lifetime. The layers of matter are blown into space, carrying carbon, oxygen, iron, the elements that will become planets, and eventually, life. But the important part is not the explosion. The crucial part is the remaining core. There, the density becomes so high that atomic structures no longer exist. Electrons are forced into protons, forming neutrons. If the core's mass is below about 2 to 3 times the Sun's mass, the neutrons can still resist gravity. The result is a neutron star, a strange object so dense that a single spoonful of its matter weighs as much as a mountain. But if the core exceeds that threshold, everything changes completely. No known physical force can halt the collapse. The core continues to shrink, surpassing any imaginable limit, until it becomes a singularity. And around that point, a boundary forms, the event horizon, where every path leads inward. That is the boundary defining a black hole. The decisive moment in a star's death actually occurs so quickly that it is almost unimaginable. Millions of years of stability, tens of millions of years of shining, and then it all ends in about a second. When nuclear reactions in the core stop, gravity immediately takes over. In the blink of an eye, an event horizon appears. A star vanishes, replaced by a black hole. For decades, we thought we understood that story. Each stellar mass black hole was believed to result from a supernova explosion. That explosion was like the universe's official announcement: a black hole has been born. Astronomers would observe the light of the supernova, measure its energy and the composition of the expelled matter, and from that infer what had happened at the star's core. But then a star system in the Large Magellanic Cloud forced us to reconsider the whole story. The binary system, named VFTS 243, contains an invisible object roughly 9 times the mass of the Sun. We know it exists because its companion star constantly wobbles as it orbits the unseen mass. Every measurement points to one conclusion: it is a black hole. The problem is, there is no trace of a supernova. If there had been an explosion, the companion star would bear chemical signatures of the ejected material, heavy elements blasted onto its surface. But the composition of this star is perfectly clean, as if it had never stood next to a gigantic blast. The orbit of the system is also too stable. Supernovae usually impart a strong kick, disturbing the orbit. Here, none of that happens. All the data point to an almost unbelievable possibility: the star collapsed directly into a black hole without ever exploding. No cosmic fireworks, no supernova, just a star vanishing. Analysis by Professor Irene Tambora at the Niels Bohr Institute indicates that the energy from the collapse did not convert into an explosion. It was carried away by neutrinos, particles that barely interact with matter. They quietly escape the star, carrying energy into space. The remaining stellar material collapsed completely, forming a black hole instantaneously. This opens an entirely new pathway for black hole formation. Some stars may not die with a bang. They simply disappear, as if they never existed, leaving behind only the distortion of space-time. And if this has happened once, it is likely happening everywhere. We just haven't noticed, because we have always been looking for explosions. How many stars have vanished this way? How many black holes have quietly formed? But the story does not end there. Recent computer simulations show another factor playing a decisive role in the collapse process: magnetic fields. Every star rotates. When a massive star begins to contract, its rotation rate increases like a figure skater pulling their arms in close to spin faster. This rapid spin generates extremely strong magnetic fields. And these fields are not passive. They actively participate in the collapse. In some cases, they can push matter outward at nearly the speed of light, preventing all of the mass from falling into the forming black hole. The magnetic pressure at this moment acts like a valve, regulating the amount of material that actually crosses the event horizon. If the magnetic field is strong, the resulting black hole will be lighter. If it is weak, more matter falls in, making the black hole heavier. But the magnetic field does another thing. It can carry away the angular momentum of the collapsing star. In other words, it drags part of the star's rotation out into space, like invisible strands stretching from the collapsing core. As a result, a black hole is defined not only by its mass, its spin rotation rate is also a critical property. And that spin is closely tied to the magnetic environment at the moment of its birth. Strong magnetic fields produce lighter and slower spinning black holes. If strong magnetic fields can hold back matter from falling into a black hole, then the opposite is also true. When the magnetic field is weak, less matter is pushed outward. More matter crosses the event horizon. The result, a heavier black hole, and often one that spins faster. This means that even in the moment a star collapses, a connection is imprinted into the black hole's structure. Its mass and spin are not random. They are determined by the physical environment in the instant of its birth. Simulations also predict another signal. When strong magnetic fields eject matter at near-light speeds, the process can produce intense bursts of radiation, gamma-ray bursts. If we could catch these gamma rays at the very moment a black hole forms, it would be direct evidence that magnetic fields play a role in its birth. In that case, we wouldn't just be inferring, we would actually be witnessing the black hole's formation. Magnetic effects also help explain something that has puzzled astronomers for years. Surveys of the universe reveal many stellar mass black holes around 10 times the mass of the Sun. At the other end of the scale, we see monstrous supermassive black holes at the centers of galaxies millions of times the Sun's mass. But between these two ranges lies a strange gap. Very few black holes exist in the range of roughly 50 to 100 solar masses. Standard stellar evolution models rarely produce objects in this range. But if magnetic fields regulate how much matter falls in and how much is ejected, they could produce exactly those black holes that fill this missing mass gap, a mechanism capable of filling the void that earlier theories left behind. And then, a recent discovery made the story even more fascinating. Data from the European Space Agency's Gaia mission revealed a star moving in an unusual way. When astronomers analyzed its motion, they realized the cause: the star is orbiting a black hole. That in itself isn't unusual, but the mass of the black hole was shocking. It weighs 33 times the mass of the Sun. For comparison, most stellar mass black holes in the Milky Way are only about 10 solar masses, even Cygnus X1. One of the most famous studied black holes is just around 21 solar masses. This new object called Gaia BH3 is significantly heavier than all of them. And, even more surprising, it lies only about 2,000 light-years away. The immediate question arose: what created a black hole this massive? The answer lies in the star that collapsed to form it. When astronomers studied its companion star in the system, they found it nearly devoid of heavy elements. In astronomical terms, it is a metal-poor star, where metals simply means all elements heavier than hydrogen and helium. This is crucial. Stars rich in heavy elements tend to lose a significant amount of mass over their lifetimes through stellar winds. Our Sun, for example, is expected to lose about half its mass before the end of its life. But a metal-poor star retains its mass much more efficiently. So when it finally collapses, the remaining matter available to form a black hole is far greater. Gaia BH3 likely formed from a star that originated very early in the universe. When heavy elements were still rare, stars like these could grow very large and keep nearly all of their mass until the final moment. And this leads to a deeper implication. The universe's first stars, called Population 3, were made only of pure hydrogen and helium. No heavy elements at all. They could be enormous, hundreds or even thousands of times the Sun's mass. When these primordial stars ended their lives, they could create black holes far more massive than the stellar mass black holes we usually see today. Those first gigantic black holes may have been the initial seeds that, over time, through mergers and accretion, grew into the supermassive black holes at the centers of galaxies. Because at the heart of galaxies, we find truly extraordinary objects, black holes, millions, even billions, of times the mass of the Sun. When astronomers began looking deeper into the universe, they discovered something almost impossible. In galaxies so distant that their light reaches us from a time when the universe was still very young, enormous supermassive black holes already existed. Some of them weigh up to 1 billion times the mass of the Sun, even though the universe at that time was only about 1 billion years old. According to everything we once believed, that shouldn't be possible. If a black hole begins its life with a mass of around 10 suns, the typical kind formed from the death of a massive star, then even if it devours matter as fast as physically possible, it still wouldn't have enough time to grow that large. The growth rate of a black hole is limited by a theoretical boundary known as the Eddington limit, where radiation pressure from infalling matter begins to push back against gravity. The calculations are straightforward. Start with 10 solar masses, grow at the maximum allowed rate, and you still cannot reach 1 billion within the time the universe allows, unless the original black hole was never small to begin with. If the starting point isn't 10 solar masses, but 100,000 or even 1 million, then the timeline suddenly makes sense. From this idea emerged two competing explanations for the origin of supermassive black holes. Astronomers call them light seeds and heavy seeds. In the light seed scenario, everything begins in a familiar way. Massive stars explode as supernovae and leave behind small black holes, roughly 10 to 100 times the mass of the Sun, over billions of years. These black holes merge with one another and continuously draw gas from their surroundings. Each merger adds more mass. Each stream of falling gas makes the black hole a little larger. Slowly, through countless mergers and steady accretion, these small black holes could eventually grow into the monsters that sit at the centers of galaxies. In theory, the story is neat and tidy, but new observations from the James Webb Space Telescope are beginning to shake that picture. Webb has repeatedly discovered supermassive black holes appearing when the universe was extremely young, so early that the slow process of mergers simply doesn't seem to have enough time to create them. As astronomer Peter von Dockum puts it, the problem is clear. Mergers take time, yet the gigantic black holes Webb is finding existed far too early in cosmic history. So astronomers have begun considering another possibility. Instead of growing slowly from tiny seeds, perhaps some black holes were born large from the very beginning. This idea is known as direct collapse. In this scenario, a massive cloud of gas does not fragment into stars as it normally would. Instead, the entire cloud collapses inward, all at once under gravity, forming a huge black hole from the start. A heavy seed, not 10 solar masses, but perhaps 100,000, or even 1 million. With a starting point like that, reaching billions of solar masses in the early universe suddenly becomes entirely possible. But direct collapse is not easy to achieve. Gas in the universe naturally tends to fragment into many smaller clumps, and those clumps form stars. For a gas cloud to collapse directly into a black hole, very special conditions are required, conditions strong enough to prevent star formation while the entire cloud continues to collapse. For decades, this remained only an idea on paper. The equations allowed it. Computer simulations suggested it could happen, but no one had ever actually seen a real example. Until the James Webb Space Telescope began surveying distant galaxies in the Cosmos Webb program. Within the data, astronomers discovered a strange galaxy with two bright cores forming a shape resembling an infinity symbol. They began referring to it simply as the Infinity Galaxy, and something unusual lies between those two cores, not inside a galactic core, where black holes normally reside, but in the space between them. There appears to be a supermassive black hole. It sits in a vast region of gas where two galaxies are colliding and merging. According to Van Dockum and his collaborators, this collision may have created the perfect conditions. Dense, turbulent streams of gas were compressed at the intersection of the two galaxies. Before the gas could fragment into stars, the entire cloud collapsed under its own gravity, a cascading collapse, leading directly to the birth of a massive black hole. If this hypothesis is confirmed, it would be the first time we have ever observed a heavy seed forming, and it would show that supermassive black holes do not necessarily have to grow slowly over billions of years through mergers. Some of them may have been born enormous from the very beginning. If supermassive black holes can be born already large, then the story of their origin may be simpler than we once thought. Recent computer simulations suggest exactly that. In 2022, a team of researchers recreated the early universe inside a numerical model, tracking how the first galaxies formed. They paid special attention to rare regions where cold streams of gas from intergalactic space continually converged at the same point. In these locations, structures known as primordial halos formed. These halos were anything but quiet. They were chaotic environments filled with turbulence and swirling flows. Yet that very chaos created something unexpected. The gas inside the halo could not settle into small clumps to form stars. It was constantly stirred and mixed. never able to stabilize into separate stellar seeds. Instead of fragmenting, the entire cloud of gas continued collapsing as one enormous mass. In the simulation, this process produced two black holes through direct collapse. One weighed about 31,000 times the mass of the Sun, the other about 40,000 times, and, remarkably, they appeared naturally within the model, without any special conditions beyond the normal laws governing cosmic structure formation. This suggests that the heavy seeds of supermassive black holes may not be rare at all. In the young universe, any sufficiently turbulent gas cloud might have been capable of producing a massive black hole from the very beginning. Over time, and those seeds could then grow into the supermassive black holes we see today at the centers of galaxies. But between the two extremes, stellar mass black holes and supermassive black holes, there remains a gap. Within that gap lies another mysterious class of objects, intermediate mass black holes. They fall in the range of 100 to 100,000 times the mass of the Sun. Too massive to form from the collapse of a single star, yet not large enough to qualify as supermassive black holes. In theory, they should exist. They are the missing bridge between the two types of black holes we already know. The problem is that they are extremely difficult to observe. As astrophysicist Manuel Arca of the Gran Sasso Science Institute explains, current observational limits make it nearly impossible to determine the population of black holes in the range of 1,000 to Daiichi 000 solar masses. They are too small to produce signals as powerful as supermassive black holes, yet they may be far more common than we realize. One of the few environments capable of creating them is extremely dense star clusters. Imagine a globular cluster, a vast spherical swarm containing hundreds of thousands of ancient stars, all packed into a relatively small region of space. At the centers of these clusters, the stellar density can be 1,000,000 times higher than in the neighborhood around our Sun. Stars there are so close together that collisions are almost unavoidable. When two massive stars collide, they merge into a larger star. The gravity of this new star then pulls in more nearby stars. The process repeats again and again, forming a chain reaction of stellar collisions. The central object grows larger each time. With every merger, its mass increases faster than before. Eventually, this process can produce a supermassive star, an object hundreds, even thousands of times the mass of the Sun. Not a supermassive black hole, but no longer an ordinary star either. Such monsters cannot survive for long. They are fundamentally unstable, and when they collapse, they may give birth to intermediate mass black holes. Recent simulations have followed this process from beginning to end. Starting from molecular clouds, researchers modeled every star as it formed, evolved, and collided inside dense star clusters. The results showed that chains of collisions can indeed create stars as massive as 300 times the mass of the Sun. Those giant stars can then merge with stellar mass black holes already present within the cluster. In one scenario, a black hole of just 12 solar masses devoured a 300 solar mass star and almost instantly crossed into the realm of intermediate mass black holes. In one simulation, the story continues even after the first intermediate mass black hole appears. About 100 million years later, it merges with another black hole, weighing 22 times the mass of the Sun. The mass of the central object keeps increasing, and interestingly, the ratio between the mass of the star cluster and the black hole at its center in the model closely matches what astronomers observe in real galaxies. That suggests intermediate mass black holes may not be rare at all. In dense stellar environments, they may form naturally and become the first seeds of supermassive black holes. But in the past few years, another factor has begun to enter the story: magnetic fields. When a massive star collapses, gravity is not the only player in the drama. The star is rotating, and within it exist powerful magnetic fields. As the core contracts, those magnetic fields can become extraordinarily intense. Simulations in 2025 show that they may launch matter outward at nearly the speed of light. This ejected material prevents the entire mass of the star from falling into the black hole that is forming. The result is a range of different outcomes. If the magnetic field is weak, most of the matter still falls inward. The newborn black hole will be heavier and spin faster. But if the magnetic field is strong, much of the material is blasted into space. The remaining black hole ends up lighter and spinning more slowly. The simulations also predict that this violent ejection of matter could produce extremely powerful gamma-ray bursts. If telescopes detect those gamma rays at the exact moment a massive star collapses, we would have direct evidence that magnetic fields are involved in the birth of black holes. This magnetic mechanism may also help explain another long-standing mystery, the black hole mass gap. When astronomers catalog known black holes, they notice a strangely empty region, between roughly 50 and 120 times the mass of the Sun. The number of black holes drops sharply. According to stellar evolution models, stars in this mass range often undergo a type of explosion called a pair instability supernova, which completely destroys the star and leaves no remnant behind. But if magnetic fields are strong enough to eject part of the star's mass during collapse, the outcome could change. Instead of being completely destroyed, the star might still leave behind a black hole right inside the mass range once thought to be forbidden. And we may already be seeing hints of this. When gravitational wave observatories such as LIGO and Virgo detect black hole mergers, some of the black holes involved have masses that fall exactly within this supposed gap. Their existence suggests that nature may have more ways of creating black holes than we once imagined. Slowly, the larger picture begins to emerge. In the early universe, metal-poor population 3 stars may have collapsed into massive black holes. Some stars may not explode at all, but collapse directly. Others may experience failed supernovae, where matter falls back inward after the initial explosion. Inside dense star clusters, chains of stellar collisions can create giant superstars, which later collapse into intermediate mass black holes. These black holes continue merging and accreting matter, growing larger over time. In rare turbulent regions of the young universe, entire gas clouds may collapse directly, forming heavy seeds, black holes, hundreds of thousands, or even millions of times the mass of the Sun from the moment they are born. Different pathways, but all leading to the same destination, the supermassive black holes at the centers of galaxies. Light seeds grow slowly through billions of years of mergers and accretion. Heavy seeds may already be enormous from the start, and intermediate mass black holes formed inside star clusters may gradually migrate toward galactic centers, helping feed those cosmic monsters. The early universe filled with metal-poor stars and turbulent rivers of gas may have been the perfect environment for all of these processes to occur, and that may explain why, when we look deep into the past of the universe, we find giant black holes appearing so early. Not all of them slowly grew from tiny remnants. Some of them may have been born enormous. The Chandra X-ray Observatory has been observing a distant galaxy cluster known as Abell 2744. Deep within that cluster, astronomers discovered a galaxy called GHZ 9, seen as it was only 450 million years after the Big Bang. At the center of GHZ 9 sits a black hole already weighing between 10 and 100 million times the mass of the Sun, just 450 million years after the universe began. This black hole had already grown enormous. The only way this makes sense is if it started big, either from direct collapse or from an unusually massive population 3 star. Small light seeds simply cannot grow fast enough to reach that size in such a short time. But what makes this discovery even more striking is something else. The mass of the black hole is comparable to the entire stellar mass of its host galaxy. in our local universe. Supermassive black holes are typically only about 1% of their galaxy's stellar mass. But in GH-SNON, the black hole's mass rivals or even exceeds the stellar mass of the galaxy itself. This suggests something extraordinary: the black hole formed first. Before significant star formation occurred in the galaxy, the black hole was already massive, while the galaxy was only beginning to assemble its stars. That's the reverse of what we usually imagine. We tend to think that galaxies form first, and then black holes gradually grow at their centers. But in the early universe, it may have happened the other way around. Massive black hole seeds formed first, and galaxies built themselves around them later. This discovery challenges our entire picture of cosmic evolution. The conventional wisdom has always been first comes the galaxy, then comes the black hole. Matter collapses into structures, stars form. Eventually, a black hole develops at the center, fed by infalling material over billions of years. But GH-9 flips that script completely. The black hole seems to have arrived first, dominating its environment before the galaxy had time to build up significant stellar mass. Think about what this means for how structure forms in the universe. If massive black holes can appear before significant galaxy formation, they might actually help trigger and shape the growth of galaxies. The black hole's gravity could draw in surrounding gas, heating it, compressing it, and possibly even regulating when and where stars begin to form. In this picture, the black hole becomes the architect of the galaxy, rather than just a tenant living at its center. And this leads to an even more important observation about the early universe. The James Webb Space Telescope hasn't found just one of these extreme cases. It is finding many of them, multiple examples of supermassive black holes appearing far earlier than our models predicted, often with unusually large masses compared to their host galaxies. This pattern suggests something profound. These may not be rare exceptions. Instead, we may be seeing a different mode of black hole and galaxy formation, one that operated in the early universe. So what made the early universe so different? Why could processes occur then that no longer happen today? The answer lies in the composition of primordial gas. The first generation of stars, known as population 3 stars, formed from gas that contained only hydrogen and helium. No carbon, no oxygen, no iron. Just the elements, created in the Big Bang itself. This pristine composition fundamentally changed how stars could form and evolve. Without heavy elements, gas clouds could not cool efficiently. In modern star-forming regions, elements like carbon and oxygen radiate energy away, allowing clouds to fragment into many smaller stars roughly the size of our Sun. But primordial gas remained hot, and hot gas resists fragmentation. Instead of breaking into many small clumps, early gas clouds could collapse as single massive objects. These first stars may have reached hundreds or even thousands of times the mass of the Sun, vastly larger than any stars forming today. When such a massive star exhausts its fuel and collapses, it does not form a 10 solar mass black hole. It forms something much larger. A population 3 star with 500 solar masses might collapse directly into a black hole of similar mass. No extended supernova, no large amount of material blown away, just a direct transformation from supermassive star to massive black hole seed. These seeds would then be perfectly positioned to grow into the supermassive black holes we observe in early galaxies. And recent simulations have begun to track the evolution of population 3 stars in unprecedented detail. Modern simulations are beginning to confirm something that theory predicted long ago. The first stars of the universe were nothing like the stars we see today. Population 3 stars were born from gas that was almost perfectly pure, containing no carbon, no oxygen, no iron, only hydrogen and helium. That simple composition caused them to evolve in a completely different way. Their cores burned hotter, their stellar winds were much weaker, meaning they did not lose most of their mass over their lifetimes the way modern stars do. And when their lives came to an end, most of that mass was still there. When they collapsed, they did not create small black holes of just a few solar masses like we typically see today. Instead, they left behind black hole seeds 10s or even hundreds of times more massive. But even this mechanism may not be the only pathway. Let's return to the chaotic primordial halos of the young universe. Simulations in 2022 traced in detail how one of these halos evolves as it is continuously fed by cold streams of gas flowing inward at high speed. These inflowing streams stir the entire halo, creating intense turbulence. And that turbulence has an unexpected effect. It prevents the gas from fragmenting into stars. Instead of settling into stable clumps, the gas is constantly mixed like a cosmic blender. But turbulence cannot fight gravity forever. As more and more gas flows inward, the mass of the halo increases. Gravity slowly grows stronger than the chaotic motion of the gas, and eventually, the entire structure begins to collapse all at once, not into a cluster of stars, but into one or two enormous objects. In the simulation, this process produced two black holes directly from gas, one weighing about 31,000 times the mass of the Sun, and another about 40,000 solar masses. There was no intermediate star phase at all, just gas, collapsing directly into black holes. And remarkably, we may already have seen this process happening in the real universe. In data from the Cosmos Web Survey, astronomers discovered a strange galactic system they nicknamed the Infinity Galaxy. Two bright galactic cores sit symmetrically, forming a shape that resembles the infinity symbol, clear evidence that two galaxies are colliding. But the most striking feature lies between them: a supermassive black hole. It does not sit in the center of either galaxy, but in the middle of a vast sea of gas surrounding the collision zone. That location is extremely unusual. Supermassive black holes almost always reside at the centers of their host galaxies, unless they were born right there. Researchers believe the galaxy collision may have created an environment that is both extremely dense and highly turbulent, similar to the primordial halos seen in simulations. The gas is too chaotic to form stars, but perfect for collapsing directly into a massive black hole. If future observations from the James Webb Space Telescope confirm this hypothesis, it would be the first time humanity has ever witnessed a direct collapse black hole forming. Not just a theory, but a process actually unfolding in the universe. Yet whether black hole seeds come from population 3 stars or from the direct collapse of gas, one major question remains. How do they grow into the monsters, weighing billions of times the mass of the Sun? A black hole of 100,000 solar masses is already impressive, but to become a billion solar mass giant, it still needs to grow 10,000 times larger, and it must do so very quickly. Black holes grow in two main ways. The first is accretion, pulling in surrounding matter. Gas, dust, and even wandering stars can fall into the black hole and become part of it. The second is mergers, when two black holes collide and combine into one larger object. But accretion has a natural limit, known as the Eddington limit. As matter falls into a black hole, it heats up violently and emits intense radiation. That radiation pushes outward against the infalling material. If the flow of matter becomes too strong, the radiation pressure can blow it away. The black hole is almost choking on its own meal. At this limit, a black hole can roughly double its mass every 50 million years. That may sound fast, but if you start from a seed of 100 solar masses, after 500 million years, it would only reach about 1 million solar masses, still far short of 1 billion. So astronomers have begun to consider a more radical possibility: super Eddington accretion. Under certain extreme conditions, the inflowing material can become so dense that it shields itself from radiation pressure. In that case, Matter can continue falling into the black hole faster than the theoretical limit once thought impossible to exceed. When matter falls into a black hole, the process does not always occur evenly from every direction. Sometimes the inflowing material arrives from a single dominant direction, creating shadows in the radiation field. Within these darker regions, additional matter can continue to fall inward more easily. The geometry of the flow begins to adjust itself in a strange way, and the system becomes self-sustaining. When that happens, the rate at which matter falls into the black hole can exceed the limit predicted by standard theory. This is known as super-Eddington accretion. In the early universe, the conditions for this process may have been far more common than they are today. The gas surrounding the first black holes was denser, and primordial halos contained enormous amounts of matter within relatively small regions of space. Turbulent streams of gas constantly poured inward, creating the perfect environment for extremely rapid growth. Instead of doubling its mass every 50 million years, a black hole born from a heavy seed might double its mass in only about 10 million years. A simple calculation shows how dramatic the effect could be. A heavy seed of 100, 0, 0, 0 solar masses, growing at 5 times the Eddington rate for 500 million years, could reach hundreds of millions of solar masses. Give it another 500 million years, and the mass could approach 1 billion solar masses. Suddenly, the timeline begins to make sense. Super-Eddington accretion provides a pathway from the massive seeds of the early universe to the gigantic supermassive black holes we observe at cosmic dawn. But accretion is not the only way black holes grow. In the early universe, galaxies were smaller and collided with each other far more frequently than they do today. Every time 2 galaxies merged, the black holes at their centers began a slow gravitational dance. They orbited each other at large distances, gradually losing energy through interactions with surrounding stars and gas. This process is known as dynamical friction. Over time, their orbits shrink. Once the distance between them becomes small enough, gravitational waves begin to carry energy away, pulling the black holes even closer together until they finally merge into a single object. Each merger can nearly double the mass of the resulting black hole if the 2 objects are similar in size. But there is a problem. The entire process from the collision of 2 galaxies to the final merger of their black holes can take hundreds of millions, sometimes even billions of years. Far too slow to explain the supermassive black holes that appear extremely early in cosmic history. That is why the most realistic scenario may involve a combination of mechanisms: massive heavy seeds, periods of super-Eddington accretion, and occasional mergers. Another clue may help us understand how these cosmic monsters grow their rotation. Black holes can spin around their axis. This rotation is measured by a parameter ranging from 0, meaning no spin at all, to uno, the maximum allowed by physics. If a black hole grows mainly through mergers, its spin is usually not extremely high. Collisions can occur from many different directions, sometimes even in opposite orientations, slowing down the overall rotation. But if a black hole grows primarily through accretion, the story is very different. Matter in the accretion disk falls inward in a consistent direction, continuously adding angular momentum and spinning the black hole up. So when astronomers observe a supermassive black hole with extremely high spin, it strongly suggests that much of its mass came from accretion. And some supermassive black holes in the early universe do indeed appear to have unusually high spins. In recent years, the James Webb Space Telescope has completely transformed our ability to observe the distant universe. Thanks to its extraordinary infrared sensitivity, JWST can peer through cosmic dust and observe galaxies that existed within the first billion years after the Big Bang. In the past, we knew of only a handful of supermassive black holes from this era. Now, they are appearing more and more frequently, and within this new data, a pattern is beginning to emerge. It isn't just GH9. Many young galaxies appear to contain black holes that are far too massive compared to the stellar mass of their host galaxies. In the modern universe, the mass of a central supermassive black hole is typically only about 0.1% of the stellar mass of its galaxy. But in the early universe, that ratio can sometimes be 10 times larger. And that is exactly what we would expect if heavy seeds were common. If a black hole begins life already massive, it will initially dominate its galaxy. But over time, as the galaxy continues forming stars and increasing its mass, that ratio gradually settles toward the familiar relationship we observe in the universe today. The overweight black holes we are seeing in young galaxies may not be strange anomalies at all. They may simply be very young black holes, appearing at a time when their host galaxies have not yet had time to grow large. If that is true, a deeper implication begins to emerge. Perhaps supermassive black holes are not the result of galaxy formation. Perhaps they are the cause. Imagine a massive black hole seed forming first. Its gravity begins pulling in surrounding gas. As matter falls inward, radiation from the accretion disk heats the environment around it. Powerful jets and winds from the black hole can blow gas out of the galaxy, regulating how much material remains available to form stars. This process is known as feedback, a key mechanism in galaxy evolution. It is the reason giant galaxies do not form stars far faster than the amount of gas they contain would allow. Until now, we assumed feedback only began after galaxies had fully formed. But observations of the early universe suggest a different scenario. It may have started from the very beginning when the first black holes appeared and began shaping their surroundings. In this emerging picture, the young universe looks almost like a factory for producing black holes. Massive population 3 stars collapse into unusually large black holes. Turbulent primordial halos collapse directly into giant seeds. Those seeds then grow rapidly through super-Eddington accretion and frequent mergers. And in some cases, the black hole may appear before the galaxy itself, becoming a gravitational anchor around which gas and stars gradually accumulate. This new theoretical framework resolves several puzzles that once troubled astronomers. It explains why we see enormous supermassive black holes so early in cosmic history. It explains why many young galaxies appear to contain black holes far heavier than expected for their size. And most importantly, it produces predictions that can be tested by future observations. Next-generation telescopes and gravitational wave detectors are gradually opening the possibility of looking even deeper into the universe's past, perhaps all the way back to the moment when the first black hole seeds were born. But to test these ideas, we must also understand something more fundamental: how black holes actually form in the present-day universe. And here, the story takes an unexpected turn. For decades, the familiar scenario seemed simple. A massive star runs out of fuel. Its core collapses. The outer layers rebound and explode outward as a brilliant supernova. The remnant becomes a neutron star. Or if the core is massive enough, a black hole. A violent ending, dramatic, and seemingly straightforward. But reality is beginning to challenge that tidy picture. In 2022, astronomers studying a binary star system known as VFTS 243 discovered something that forced scientists to reconsider the model. The system contains a normal star orbiting a black hole roughly 9 times the mass of the Sun. That alone is not unusual. But when researchers traced back the history of the system trying to reconstruct how it formed, a strange detail emerged. There was no evidence of a supernova explosion. The progenitor star does not appear to have exploded at all. No shell of material blasted into space. No bright remnant left behind. It simply collapsed directly into a black hole. Almost all of its matter fell inward, leaving very little material to escape. The star essentially vanished from the sky, leaving behind only the gravitational trace of the black hole. Professor Irene Tambora of the Niels Bohr Institute led the analysis, confirming this scenario what astronomers call a failed supernova. The key clue lies in the orbit of the binary system. When a star explodes as a supernova, the explosion is usually not perfectly symmetrical. That asymmetry produces a natal kick, a recoil that can send the newborn black hole flying through space at speeds of hundreds of kilometers per second. This kick often distorts the orbit of the binary system, or even destroys it completely. But in VFTS 243, the orbit remains almost perfectly circular. And that can only happen if the collapse occurred almost perfectly symmetrically, with most of the star's mass falling straight into the black hole, rather than being blasted outward in an explosion. When a massive star collapses, the energy involved in that process does not simply disappear. It escapes in the form of neutrinos, particles that interact so weakly with matter that they can pass almost unhindered through an entire star. In a typical supernova, the energy carried away by neutrinos is precisely what helps blow apart the outer layers of the star, creating the brilliant explosion we observe from across the universe. But in the case of VFTS 243, something very different happened. The collapse occurred too quickly, too completely. Neutrinos carried energy away from the core before enough of that energy could be transferred to the outer layers of the star. No explosion was triggered. No stellar envelope was blasted into space. The star simply vanished. This silent collapse scenario may not be as rare as we once believed. When astronomers examine binary systems containing black holes, they notice that many of them have almost perfectly circular orbits. If an asymmetric supernova had occurred, the newborn black hole would typically receive a strong recoil known as a natal kick, which distorts the orbit, or sometimes even disrupts the binary system entirely. But many systems show no evidence of such a kick. This suggests that a large fraction of black holes may have formed through failed supernovae, where a star collapses directly into a black hole without exploding. Some estimates even suggest that nearly half of all stellar mass black holes may be born this quiet way. Yet the story contains another ingredient that makes things even more complex: magnetic fields. Inside massive stars, strong magnetic fields already exist. As the core collapses and begins spinning faster, those fields become compressed and amplified, growing extraordinarily intense. Recent simulations show that they can generate narrow jets of matter that shoot out along the star's rotation axis at nearly the speed of light. These jets do more than carry energy away. They carry mass and angular momentum as well, and that dramatically changes the properties of the black hole that forms. If the magnetic fields are strong, the jets eject more matter outward. Material that would otherwise fall into the black hole is instead blasted into space. The resulting black hole ends up less massive. At the same time, because the jets also remove angular momentum, the newborn black hole spins more slowly. But if the magnetic fields are weaker, far less matter is expelled. The black hole retains more mass and more of the star's original angular momentum. In other words, the strength of magnetic fields at the moment of collapse may determine both the mass and the spin of the newborn black hole. This leads to an intriguing prediction. Black holes may follow a relationship between mass and spin, heavier black holes tending to rotate faster, while lighter ones spin more slowly. Gravitational wave observations have only begun to test this prediction, but the first hints are already intriguing. Magnetic jets may also produce another spectacular consequence. As they punch through the collapsing star's outer layers, they can generate extremely powerful gamma-ray bursts. Some of the most energetic explosions in the universe may actually come from failed supernovae, where the star does not fully explode, yet the jets still erupt violently. This magnetic mechanism might even help explain another long-standing mystery: the black hole mass gap. Observations show that very few black holes appear in the range of 3 to 5 solar masses. According to stellar evolution models, Stars in this regime tend to leave behind either neutron stars below 3 solar masses or black holes above 5, leaving almost no objects in between. But if magnetic jets can eject varying amounts of mass during collapse, the final mass of a black hole could land precisely within this forbidden region. A star might begin collapsing toward a larger black hole, but powerful jets could blow away enough mass that the final black hole ends up between 3 and 5 solar masses. We have not yet confirmed such objects, but theoretical models suggest they should exist. Today we know that stellar mass black holes can form through at least 2 different pathways. Some are born from core collapse supernovae, where the outer layers of a star are violently expelled. Others emerge through direct collapse, when the entire star falls inward almost silently. And in both cases, magnetic fields may play a crucial role in determining the final mass and spin of the newborn black hole. But even the largest black holes formed from stars remain tiny compared to the monsters that sit at the centers of galaxies. Which brings us back to the fundamental question: how do we go from a black hole of 10 solar masses to objects weighing billions of times the mass of the Sun? One simple possibility is this: perhaps we never started that small. And that is where another class of objects enters the story: intermediate mass black holes. The missing bridge between stellar mass black holes and the enormous supermassive giants. In the universe, black holes do not arise from a single pathway. Each environment, each cosmic era, opens a different route for their creation. Stellar mass black holes appear wherever a massive star reaches the end of its life. Intermediate mass black holes require dense star clusters, where stars collide and merge again and again, and the giant seeds born from the direct collapse of gas could only form in the metal-poor primordial conditions of the early universe. Because of this, the supermassive black holes we observe today may carry very different histories. Some appear to have begun as enormous heavy seeds. Others may have started more modestly and grown over billions of years through accretion and mergers. Some galaxies host intermediate mass black holes that never grew further. And there are even galaxies that show no sign of a central black hole at all, despite containing substantial stellar mass. Understanding these pathways is not simply a matter of classifying different types of black holes. It connects directly to how the universe builds structure, how galaxies form, evolve, and connect into the vast cosmic web we observe today. Because black holes do not simply appear and remain passive. From the moment they are born, they begin to reshape their surroundings. The instant the core of a massive star collapses is not a quiet disappearance. Matter from the outer layers plunges inward at speeds approaching a significant fraction of the speed of light. When that infalling material crashes into the region near the forming event horizon, it releases an enormous amount of energy. Some of that energy escapes as neutrinos, almost invisible particles that pass easily through matter. Another portion emerges as narrow jets of matter, launched along the magnetic field lines of the star. These jets drill through the collapsing stellar envelope, punching through thousands of solar masses of material in just seconds. The violent birth of a black hole leaves traces that we can still detect billions of years later. As matter continues to fall toward the newborn black hole, it cannot plunge straight inward. Because of the conservation of angular momentum, the inflowing material forms a vast rotating structure around the black hole, an accretion disk. Friction between layers of matter within the disk heats it to temperatures of millions of degrees. At such temperatures, the matter radiates across almost the entire electromagnetic spectrum: radio waves, infrared, visible light, X-rays, and even gamma rays. A strongly accreting black hole can shine brighter than its entire host galaxy, even though the black hole itself may be smaller than our solar system. What is remarkable is that this energy does not come from the black hole itself. The event horizon allows no radiation to escape from inside. The energy we observe actually comes from the gravitational energy of matter falling inward. As material spirals closer to the black hole, Its gravitational energy is converted first into motion, and then into heat through friction. Near the innermost stable orbit, nearly half of the mass energy of the infalling matter can be converted into radiation. This efficiency far exceeds nuclear fusion in stars, which converts less than 1% of mass into energy. It is precisely this extraordinary efficiency that makes supermassive black holes such powerful agents in the evolution of galaxies. When a supermassive black hole at the center of a galaxy accretes matter rapidly, it produces powerful winds and outflows that sweep through the galaxy. These winds can remove or heat the gas, the raw material needed to form stars, effectively shutting down star formation for millions of years. Astronomers call this process feedback, and it plays a crucial role in explaining why the largest galaxies do not form stars as rapidly as simple models once predicted. Without black hole feedback, the most massive galaxies in the universe should contain far more stars than they actually do. Instead, observations show that once a galaxy's mass exceeds roughly 1 trillion times the mass of the Sun, such galaxies become increasingly rare. The supermassive black holes at their centers appear to halt further growth by pushing away or heating the gas needed for star formation. The result is a self-regulating cycle. As a galaxy grows, the black hole at its center grows as well. The increasing mass strengthens the gravitational pull, drawing more gas toward the center, and the cycle of influence between black hole and galaxy continues. As a black hole pulls in more and more gas, the energy it releases increases as well. Powerful winds begin to blow through the galaxy, sweeping away the gas, the very raw material needed to create new stars. Gradually, star formation slows and eventually stops. The galaxy grows quiet, and as the supply of gas runs out, the central black hole itself falls into a dormant state, as if it has regulated its own food source. Recent observations from the James Webb Space Telescope are showing that the relationship between galaxies and black holes began very early. Astronomers have discovered supermassive black holes that already existed when the universe was less than 1 billion years old, and some of them already weighed billions of times the mass of the Sun. At such early times, their host galaxies were still in the earliest stages of formation. In some cases, the mass of the black hole is equal to, or even greater than the total stellar mass of the galaxy. This is the opposite of what we see in the modern universe, where supermassive black holes usually account for only about 1/1000th of the stellar mass of their galaxies. This reversed ratio suggests something profound about how the first galaxies formed. It may be that black holes appeared before galaxies had time to build many stars. These enormous seeds could then begin shaping the growth of the galaxy through their feedback effects. Another possibility is that black holes and galaxies grew from the same underlying processes. But in the early stages, the black hole simply grew faster than the stellar component. The answer to this question is not a minor detail of astronomy. It determines how we understand the formation of structure in the universe. If black holes come first, they are engines driving galaxy evolution from the very beginning. If galaxies come first, black holes are merely a byproduct of that process. Recent evidence is increasingly leaning toward the first possibility. Black holes formed through direct collapse may appear only a few 100 million years after the Big Bang. These heavy seeds begin accreting gas and influencing their surroundings very early, even before the first generation of stars has completed its life cycle. But directly observing these processes is extraordinarily difficult. The first supermassive black holes lie at immense distances, where their light has traveled more than 13 billion years to reach us. During that journey, the expansion of the universe stretches the wavelength of the light. Radiation that was originally emitted in the ultraviolet or visible range arrives at Earth, shifted into the infrared. Only space telescopes designed specifically for infrared observations, like JWST, can see them clearly. Even then, we do not observe the black hole itself. What we see is its effect on surrounding matter. When gas falls into a supermassive black hole, the accretion disk around it heats up and begins to shine intensely. The active centers of galaxies, known as AGN, or active galactic nuclei, can shine brighter than all the stars in their host galaxy combined. Among these objects, the brightest examples are known as quasars. When quasars were first discovered in the 1960s, they puzzled astronomers. They appeared as tiny points of light, similar to stars, but their spectra revealed that they were located at enormous cosmic distances. To be visible from such distances, they had to emit an almost unimaginable amount of energy. The only plausible explanation was that supermassive black holes at their centers were devouring matter at extraordinary rates. Each quasar represents a black hole in a violent feeding phase, swallowing material equivalent to several solar masses every year. But this outburst cannot last forever, as the black hole gradually consumes the surrounding gas. The supply of fuel declines, the accretion rate drops, the brightness fades. Eventually, the quasar phase ends, leaving behind a quiet supermassive black hole in a galaxy that has lost much of its gas. This is why many large galaxies in the modern universe contain central black holes that are almost completely inactive. Their brilliant phase occurred long ago, and they have already consumed most of the fuel around them. However, this quiet state is not always permanent. When two galaxies collide, gravity can funnel gas toward the center once again, triggering a new phase of accretion. And if both galaxies contain supermassive black holes at their centers, those two black holes will eventually merge with each other. When two black holes draw close to one another, their merger is not silent. The event shakes the very fabric of space-time itself. Energy and angular momentum are carried away as gravitational waves, ripples that propagate across the universe. Over the past decade, detectors such as LIGO and Virgo have opened a new era of astronomy. They have recorded dozens of mergers between stellar mass black holes, ranging from a few solar masses to nearly 100. But when the monsters at the centers of galaxies collide, the story is different. Supermassive black holes emit gravitational waves at much lower frequencies, so low that detectors on Earth cannot hear them. To detect the sound of such events, we will need observatories in space. One of the most important missions designed for this purpose is LISA, planned for launch in the 2030s. As two supermassive black holes spiral toward each other, they emit gravitational waves that grow steadily stronger. The signal increases both in frequency and intensity, producing a characteristic pattern known as a chirp. In the final moment, the two event horizons merge into one. In a fraction of a second, the energy released in gravitational waves can exceed the light emitted by all the stars in the observable universe during that same instant. After the collision, the newborn black hole does not immediately settle. It vibrates like a bell that has just been struck. This stage, called the ring down, produces distinctive gravitational wave oscillations. Those oscillations carry precise information about the mass and spin of the final black hole. By analyzing this signal, astronomers can measure supermassive black holes billions of light-years away with remarkable accuracy. Gravitational wave astronomy does not replace traditional observations, it complements them. Light shows us the environment around black holes, the hot gas in accretion disks, dust, stars, and enormous jets of matter. Gravitational waves reveal the black holes themselves, their masses, their spins, and how they moved before merging. Two different windows onto the universe. But when combined, they form a far more complete picture of a black hole's life. In that picture, the deaths of massive stars create stellar mass black holes. Dense star clusters build intermediate mass black holes through chains of collisions and mergers. And in the early universe, giant clouds of gas may collapse directly, producing massive seeds. All of these pathways ultimately converge toward the same outcome: the formation of supermassive black holes at the centers of galaxies. What makes this especially fascinating is that each pathway leaves behind its own fingerprints. Black holes born from supernovae often carry strong natal kicks, caused by asymmetric explosions. Black holes formed through direct collapse receive almost no kick at all, and therefore tend to remain bound in tight binary systems. Intermediate mass black holes formed in star clusters may retain evidence of multiple mergers in their spin, and seeds created through the direct collapse of gas may appear extremely early in cosmic history, already weighing thousands of solar masses when the universe was less than 1 billion years old. To test all these predictions, astronomers must use every observational tool available. X-ray telescopes reveal hot gas swirling around black holes. Infrared observations peer through cosmic dust to uncover hidden active galactic nuclei. Radio telescopes trace jets of matter stretching millions of light-years from galactic centers. And gravitational wave detectors capture mergers that light alone cannot reveal. Each method provides only one piece of the puzzle, but when those pieces are assembled, they begin to tell a complete story. The story of how black holes are born, grow, and ultimately shape the universe we inhabit. The coming decade may completely transform the way we understand black holes. The James Webb Space Telescope continues to look deeper into the universe's past, discovering black holes that are increasingly distant and increasingly massive. Meanwhile, the Extremely Large Telescope, soon to begin operations, will have an unprecedented angular resolution, allowing us to observe the detailed structures near supermassive black holes in galaxies at enormous distances. At the same time, an entirely new observational window is about to open. The LISA mission will place gravitational wave detectors in space, where they will be able to hear vibrations that detectors on Earth cannot perceive: gravitational waves produced when supermassive black holes merge. Alongside these new telescopes and detectors, computer simulations are also advancing rapidly. Increasingly detailed models can now recreate entire chains of events, from the collapse of a single star to the formation of an entire galaxy. These tools promise to answer a series of fundamental questions. How many different pathways lead to the birth of black holes? How many supermassive black holes began as heavy seeds? And how many grew from smaller light seeds? In what ways do central black holes regulate the rate of star formation in their galaxies? And what role did they play in the reionization of the early universe, the era when the first light began, to pierce the darkness following the Big Bang? Each answer will help us better understand how the structure of the universe emerged from an almost uniform state shortly after the Big Bang. But the closer we come to answers, the deeper the mysteries become. Why is the mass of a black hole so tightly linked to the mass of its host galaxy? What determines whether a collapsing cloud of gas will produce stars or a black hole? And how could supermassive black holes grow so extraordinarily fast during the universe's first billion years? These questions lead directly to the frontiers of physics. They involve the nature of gravity, the behavior of matter at extreme densities, and the strange quantum properties of event horizons. For that reason, studying black hole formation is not just astronomy. It is a way of probing physics in its most extreme states. One of the deepest mysteries began with a discovery by Stephen Hawking. He showed that black holes are not entirely black, due to quantum effects at the event horizon. They emit an extremely faint form of radiation now known as Hawking radiation. That discovery immediately created a paradox. According to quantum mechanics, information cannot be destroyed. But Hawking radiation is thermal in nature, seemingly containing no information about the matter that fell into the black hole. If the black hole eventually evaporates completely, that information appears to disappear. This is the information paradox, a problem that has driven theoretical physics for decades. One of the boldest ideas suggests that the information of everything falling into a black hole is actually stored on its surface. According to the holographic principle, all the information contained in a three-dimensional space could be encoded on a two-dimensional surface. If that is true, then when a star collapses into a black hole, the three-dimensional structure of the matter might be translated into a two-dimensional form of information on the event horizon. Another approach turns to quantum entanglement. When matter falls through the event horizon, particles may become entangled with particles that form Hawking radiation outside the black hole. These subtle quantum correlations could preserve information even as the classical structure of matter disappears into the singularity. If so, the entire information about the matter that fell into the black hole may still exist, encoded within extremely delicate quantum correlations between the radiation and the black hole's interior. But to test these ideas, we need to observe black holes at the moment they are born. Gravitational waves emitted during the formation of a black hole may carry tiny signatures of quantum effects. Gamma-ray bursts accompanying stellar collapse might also contain similar signals if measured with sufficient precision. In the future, detectors sensitive to high-frequency gravitational waves might even detect quantum fluctuations of space-time itself as a star collapses. If that happens, we will not merely observe the birth of black holes. We may be witnessing quantum gravity in action before our eyes. And as the story goes deeper, physicists have realized that the connection between black holes and thermodynamics runs even deeper than Hawking radiation itself. One of the strangest things about black holes is how they store information. In most physical systems, entropy, a measure of disorder, scales with volume, but for black holes, entropy scales with the surface area of the event horizon. This suggests a profound idea: the fundamental information of the universe may not reside in three-dimensional space as we usually imagine. It may be encoded on two-dimensional surfaces. Every time a black hole forms, a new event horizon appears. The entropy of the universe increases. In that sense, the birth of a black hole is not merely an astronomical event. It also helps shape the arrow of time, the reason the universe always evolves toward greater disorder. From a thermodynamic perspective, the different pathways leading to black hole formation are not equally likely. Some pathways generate entropy more efficiently than others. The direct collapse of matter represents the most extreme case. A complex structure like a star is transformed almost entirely into event horizon area, the most efficient possible conversion of information into entropy. Failed supernovae with fallback material lie somewhere in between. Part of the star's structure is disrupted, but some of it persists for a time before eventually falling into the black hole. Successful supernova explosions that leave behind neutron stars preserve even more order. Information about the structure of matter remains within the extremely dense neutron core instead of being hidden behind an event horizon. During collapse, the star's magnetic field may play an unexpected role. As the core contracts and spins faster, magnetic field lines become extraordinarily strong. Some models suggest that these magnetic fields could leave an imprint on the event horizon as it forms. If that is true, the structure of a black hole may not be completely simple, not fully described only by its mass and spin. Subtle traces of the original magnetic field might persist as tiny deviations in Hawking radiation or in the geometry of the event horizon. Detecting such signatures would be a major breakthrough. It would suggest that information about the original star does not completely disappear when a black hole forms. In this picture, the spin of the black hole becomes particularly important. A rapidly rotating black hole is very different from a non-rotating one. Around it exists a region called the ergosphere, where space-time itself is dragged into rotation. How a black hole is born, whether slowly or violently, with strong or weak rotation, may determine the quantum state of the event horizon, and the spin imprinted in that moment of formation could influence how information escapes through Hawking radiation billions of years later. Population 3 stars from the early universe offer a natural laboratory for studying this. They were born when the universe was still pristine. containing only hydrogen and helium left over from the Big Bang. When these massive stars collapsed, they produced the first black holes in the universe. Because their chemical composition was extremely simple, the black holes formed from them may possess quantum properties different from those of black holes born from today's metal-rich stars. Comparing these two types of black holes could reveal how the chemical composition of matter affects the formation process at the quantum level. Meanwhile, another mystery is slowly narrowing. The boundary between neutron stars and black holes is no longer as clear as it once seemed. Recent observations have discovered objects with masses around 2.5 times that of the Sun, right in the transition region between the two categories. They might be the lightest black holes ever formed, or they could be neutron stars containing a completely different state of matter from ordinary nuclear matter. The answer depends on how they were born. Fallback supernovae provide clues. In some explosions, material is ejected from the star, but does not have enough energy to escape entirely. Part of it falls back onto the core. If enough material returns, it can push a neutron star beyond the maximum stable mass, causing it to collapse into a black hole. This transition can occur extremely quickly, within milliseconds, but in other cases it may take several seconds, or even hours. Each scenario leaves different signatures in the light of the supernova and in the chemical composition of the surrounding environment. To test these ideas, astronomers often turn to binary star systems. When one star in a binary system becomes a black hole while the other remains normal, the orbit of the system becomes an extraordinarily precise measuring tool. From the motion of the companion star, we can infer the mass and properties of the black hole. At the same time, that companion star also preserves traces of the event that created the black hole. If the original supernova explosion was asymmetric, it can produce a natal kick, a powerful jolt that alters the orbit of the binary system. And within those subtle changes in the orbit, the history of the black hole's formation remains recorded. Sometimes, the trace of a black hole is not found within the black hole itself, but in the orbit of the star beside it. When astronomers measure the eccentricity of an orbit in a binary system, they can trace back the kick velocity the black hole received at birth, a crucial clue revealing whether the parent star exploded as a supernova or simply collapsed directly into darkness. The system VFTS 243 is an almost perfect example of this kind of investigation. In that system, a black hole and a massive star orbit each other in an almost perfectly circular path. If an asymmetric supernova explosion had occurred, the kick from that explosion should have distorted the orbit. But that did not happen. The quiet, circular orbit tells a different story. The star collapsed directly into a black hole, with most of the energy carried away by neutrinos rather than matter blasted into space. A nearly silent death, no cosmic fireworks, just the entire mass of the star falling straight into a gravitational abyss. Those neutrinos hold the key to the final moment. During the collapse of the stellar core, they escape before the event horizon fully forms, carrying information about the final nuclear reactions taking place inside the core. In 1987, underground detectors recorded a burst of neutrinos from supernova 1987A, confirming this process in the case where a neutron star was born. If a star in the Milky Way collapses into a black hole in the future, its neutrino signal will be both familiar and different. The energy spectrum and duration of the signal could reveal whether the collapse occurred directly or involved fallback material, how rapidly the parent star was rotating, and which nuclear reactions occurred in the contracting core. Neutrino observatories such as IceCube are patiently waiting for that moment. When a sufficiently nearby stellar collapse occurs, thousands of neutrinos will be detected almost simultaneously, outlining the formation of a new compact object in remarkable detail. And if the final outcome is a black hole, the signal will abruptly cut off the moment the event horizon forms, Unlike the longer neutrino emission from a proto-neutron star, that difference of just a few seconds is enough to distinguish between two completely different stellar fates. But sometimes the history of the collapse is recorded not in neutrinos or orbits, but on the surface of the surviving star. In a binary system, if a massive star explodes as a supernova, the heavy element-rich ejecta from the explosion will fall onto the companion star. In that case, its spectrum should show excesses of elements such as oxygen, magnesium, and silicon. If no explosion occurred and the star simply collapsed into a black hole, the surface of the companion star will retain its original chemical composition. Spectroscopic observations of binary systems containing black holes therefore become archival records of their formation. The case of Gaia BH3 is a notable example. Its companion star shows low metallicity, consistent with the hypothesis that metal-poor stars lose less mass through stellar winds and can therefore produce heavier black holes. The connection between the chemical composition of the companion star and the mass of the black hole becomes an important test for models of stellar evolution. If many massive black holes are indeed paired with metal-poor stars, it suggests that the first stars in the universe may have left behind a population of unusually heavy stellar black holes. In dense, globular clusters, the story becomes even more complex. When many stellar mass black holes form within the same cluster, they gradually sink toward the center through dynamical friction. There, gravitational interactions act like cosmic slingshots, often ejecting them from the cluster. But sometimes, before being thrown out, two black holes merge with each other, forming a heavier black hole that continues to sink quietly toward the heart of the cluster. At the centers of dense globular clusters, small black holes do not remain still. They gradually gather together, encountering one another in violent gravitational interactions. Most are flung outward, but occasionally two black holes merge before being ejected. Repeated enough times, this hierarchical chain of mergers can build an increasingly massive black hole, gradually moving into the intermediate mass range. The outcome of this process depends on the cluster itself, its initial stellar density, its total mass, and even its metallicity. Each time two black holes collide, they carry angular momentum that alters the spin of the newly formed object. But at the same time, the gravitational waves emitted during the merger carry away part of that spin. The tug-of-war between these two effects determines whether the growing black hole will spin faster or gradually slow down with each merger. As a result, theoretical models predict very specific relationships between the mass and spin of black holes formed through this pathway. Future gravitational wave observations will test these predictions and reveal whether intermediate mass black holes in globular clusters truly arise from runaway merger chains. In another direction, the physics of star formation itself sets clear mass limits for stellar black holes. Stars with masses roughly between 130 and 250 times that of the Sun are predicted to undergo pair instability supernovae explosions that completely destroy the star, leaving no remnant behind. Below this range, ordinary core collapse typically produces black holes of a few tens of solar masses, perhaps up to about 50 or 60. But if the mass exceeds this unstable region, the star may collapse directly, producing black holes larger than about 250 solar masses. These numbers turn black hole mass measurements into a direct test of theory. Gaia BH3, with about 33 solar masses, lies comfortably within the allowed range. However, a few gravitational wave signals have hinted at black holes that appear within the predicted gap where theory says they should not exist. Such objects raise an important question. Did they form directly from stellar collapse, or were they gradually assembled through mergers? A key clue lies in spin. If a black hole forms from the collapse of a single star, its spin axis will usually align with the rotation of its parent star. But if it is the product of mergers, the spin direction is likely to be far more chaotic and unpredictable. As gravitational wave detectors become more sensitive, measurements of black hole spins will reveal whether the pair instability gap truly contains black holes, and if so, how they were born. But not every black hole begins with a star. In the early universe, another pathway may have existed. If a primordial gas cloud collapsed without fragmenting into individual stars, the entire cloud could fall directly into a massive black hole, with a mass ranging from thousands to millions of suns. For this to occur, the environment must be very special. Intense radiation prevents the gas from cooling and fragmenting into stars. Turbulent flows inhibit fragmentation, and dark matter halos large enough to keep the entire gas cloud bound by gravity. Computer simulations show that such conditions could arise naturally, though only in rare regions of the young universe. A recent discovery in the Infinity Galaxy may be evidence of this process. The supermassive black hole there does not lie at the center of a galaxy, but instead sits between the cores of two interacting galaxies, surrounded by dense clouds of gas. This unusual location matches predictions for a direct collapse scenario during a galactic collision. When galaxies press into each other, the gas between them is violently compressed, becoming dense and turbulent conditions that may allow it to collapse directly into a massive black hole. Further observations measuring the black hole's mass, the properties of the surrounding gas, and the dynamics of the galactic merger will determine whether this explanation is correct. Beyond all these scenarios, an even stranger possibility remains. In the very first moments of the universe, if density fluctuations were large enough, a region of space could collapse directly into a black hole before any stars had time to form. These primordial black holes could span an enormous range of masses, from extremely tiny objects to thousands of solar masses, depending on when they formed. If enough of them exist, they might even contribute to the dark matter of the universe. A few unexpectedly heavy black hole mergers detected through gravitational waves have revived interest in this idea. Yet distinguishing them from black holes formed from stars remains extremely difficult. The cosmic microwave background places an important constraint if too many primordial black holes formed in the early universe. They would leave a clear imprint by distorting the ancient radiation pattern that we observe today. If primordial black holes truly exist, they may account for only a fraction of dark matter, but that fraction could still be large enough to influence the history of the universe. Future measurements of the gravitational wave background and the formation of matter structures on small scales will gradually narrow down this possibility, revealing whether black holes born in the very early universe contribute significantly to the black hole population we observe today. The answers lie not only in the masses of black holes, but also in how they spin. The spin of a black hole carries traces of its past direct stellar collapse. Fallback supernovae, or chains of binary mergers, each leave different signatures. As gravitational wave detectors such as LIGO, Virgo, and CAGRA record more and more mergers, the statistical picture of their masses and spins begins to reveal the dominant formation pathways. Early results suggest that reality is more complex than expected. Both rapidly spinning and slowly rotating black holes appear within the same population. Next-generation detectors will push this survey much further. The Einstein telescope and Cosmic Explorer will observe mergers at much higher redshifts. Looking back to the young universe when the conditions for black hole formation were very different from those today. Meanwhile, the LISA mission will track mergers of supermassive black holes, helping determine whether they grew from small seeds born from stars or from massive seeds formed directly in the early universe. Each gravitational wave signal recorded is like a new piece in the long story of the origin of black holes. Today, the detection of black holes no longer relies on theoretical speculation alone. Multiple observational methods are painting an increasingly detailed picture of them. When matter is pulled into the enormous gravitational field of a black hole, it is compressed and heated to millions of degrees, emitting X-rays that can be observed across interstellar distances. In X-ray binary systems, matter from the companion star spirals through an accretion disk before falling across the event horizon, producing characteristic flickering variations in brightness. These systems often remain quiet for long periods, then suddenly flare up when the accretion rate surges, increasing their brightness thousands of times. The rhythm of these variations reveals the mass and rotation of the black hole hidden within. At optical wavelengths, black holes are recognized in another way through their gravitational influence. In a binary system, if a star orbits an invisible object, it will wobble back and forth around the shared center of mass. By measuring the amplitude and period of that motion, astronomers can calculate the mass of the unseen companion. If the value exceeds the maximum mass of a neutron star, roughly 3 times the mass of the Sun, the object is almost certainly a black hole. This method led to the confirmation of the first stellar black hole, Cygnus X zone, Inch 1964, when radio and optical observations revealed a supergiant star being tugged by an invisible but extremely massive companion. More than half a century later, the European Space Agency's Gaia mission has taken this technique to a new level. By measuring the positions and motions of billions of stars in the Milky Way with unprecedented precision, Gaia can detect extremely small stellar wobbles. One such wobble led to the discovery of Gaia BH3, a star orbiting a 3.3 solar mass black hole with a period of 11 years, the most massive stellar black hole ever identified in our galaxy. At radio wavelengths, black holes reveal their presence in an even more spectacular way. As matter spirals through the accretion disk, powerful magnetic fields can launch narrow beams of particles and radiation perpendicular to the disk. These jets travel at nearly the speed of light, emitting synchrotron radiation detectable by radio telescopes. From stellar black holes in the Milky Way to supermassive black holes in distant galaxies, such radio jets can stretch for thousands of light years. By linking radio telescopes across continents, the Very Long Baseline Array achieves enough resolution to observe the structure of these jets extremely close to the event horizon. Then, in 2019, a breakthrough that once seemed impossible occurred. The Event Horizon Telescope network spanning the entire planet functioned as an Earth-sized telescope. The result was the first image of a black hole's shadow in the galaxy, M87, a bright ring of light surrounding a deep, the dark region at the center, a direct imprint of the place where light itself cannot escape. The 2019 image did more than show a ring of light surrounding a dark region. It revealed the shadow of a black hole imprinted against the backdrop of a violently glowing accretion disk. The size of that dark region matched remarkably well with what Einstein had predicted about the curvature of space-time in an extreme gravitational field. A few years later, astronomers turned the global telescope network toward the center of the Milky Way. There, Sagittarius, A times the supermassive black hole at the heart of our own galaxy, appeared with a similar structure, even though its mass is millions of times smaller than the black hole in M87. But light is not the only way to detect black holes. In 2015, an extraordinarily faint signal passed through Earth, shaking the laser interferometers of LIGO. Gravitational waves from a black hole merger stretched and squeezed the detector arms by less than a fraction of a proton's diameter. Hidden within that signal was the story of 2 black holes, 36 and 29 times the mass of the Sun, spiraling faster and faster around each other until they merged into a single object of 62 solar masses. In the final instant alone, energy equivalent to 3 suns was released as gravitational waves. Since that first signal, detectors have recorded hundreds of mergers. Most involve black holes with masses between about 7 and 50 solar masses, consistent with predictions from stellar evolution models. But occasionally the data reveal something unexpected. The event GW190521 showed two black holes weighing 85 and 66 solar masses, both within the so-called pair instability gap, where theory suggests black holes should not form from stellar collapse. When they merged, the result was a black hole of 142 solar masses, the first direct observational evidence for an intermediate mass black hole. Discoveries like this force physicists to rethink their assumptions. Perhaps some extremely massive stars collapse directly into black holes, bypassing the instabilities that should cause them to explode. Or perhaps these enormous black holes are built gradually through repeated mergers of smaller ones. To distinguish between these scenarios, scientists look for a subtler clue: spin. The direction and speed of a black hole's rotation carry information about how it formed. Next-generation detectors will expand this investigation across the entire universe. The Einstein Telescope and Cosmic Explorer are expected to increase sensitivity by roughly an order of magnitude, allowing the detection of black hole mergers at enormous distances, even from the very early universe. The black holes observed then will carry traces of the first stars, the population 3 stars formed from primordial hydrogen and helium, before the universe contained heavier elements such as carbon, oxygen, or iron. In the 2030s, a completely different instrument will join this search. LISA, the Laser Interferometer Space Antenna, will consist of 3 spacecraft separated by 2.5 million kilometers, forming a gigantic interferometer in space. Unlike ground-based detectors, LISA will observe low-frequency gravitational waves lasting from minutes to hours, produced when supermassive black holes, millions to billions of times the mass of the Sun, merge during galactic collisions. These observations will reveal whether giant black holes grew from small seeds or from massive seeds formed directly in the early universe. Even without gravitational waves or direct images, black holes can reveal themselves in another dramatic way. Sometimes a wandering star passes too close. The black hole's tidal forces stretch it like a strand of cosmic spaghetti, compressing and pulling until the star is torn apart completely. Roughly half of the star's material is flung back into space, but the rest falls toward the black hole, spiraling inward and flaring brilliantly. For months, even years, a powerful burst of optical and X-ray light marks the place where a star once existed before being swallowed by the darkness. Sometimes, a wandering star passes too close to a black hole and is torn apart by tidal forces. These tidal disruption events leave behind flares that can last for months or even years. From the shape and brightness of these flares, astronomers have recorded dozens of such events and used them to measure the masses and spin rates of black holes hidden in galactic cores. The frequency of these stellar disruptions also reveals how many black holes reside at the centers of galaxies. But to look further back in cosmic history, astronomers turn to quasars. These sources shine so brightly that they can outshine an entire galaxy. Powered by supermassive black holes at their centers, devouring matter at enormous rates. Some of the most distant quasars we observe emitted their light when the universe was less than 1 billion years old, only about 7% of its current age. Yet even at such an early time, they already contain black holes billions of times the mass of the Sun. This extraordinary growth rate is difficult to explain with ordinary accretion models, leading scientists to consider the possibility of massive black hole seeds from the very beginning, or prolonged periods of super-Eddington accretion. The Chandra X-ray Observatory has pushed this time boundary even further. While observing the galaxy cluster Abell 2744, a massive gravitational lens magnifying background galaxies, astronomers detected X-ray radiation from galaxies that existed only about 450 million years after the Big Bang. Their brightness suggests that the black holes within them had already reached masses between 10 and 100 million solar masses. If confirmed, these would be the earliest supermassive black holes ever discovered, appearing when the universe was only about 3% of its present age. strong evidence supporting the heavy black hole seed scenario. Not only the light from black holes tells their story, the chemical composition of nearby stars also preserves clues. When massive stars explode as supernovae, they scatter heavy elements into the interstellar medium. Later generations of stars inherit these chemical signatures. In the Gaia BH3 system, the companion star of the black hole has extremely low metallicity, almost devoid of heavy elements. This suggests that the black hole formed from a metal-poor parent star. According to theory, such stars lose less mass through stellar winds and can therefore collapse into heavier black holes. This connection links the story of black holes with the chemical history of galaxies in the early universe. Every star formed from primordial gas, composed only of hydrogen and helium. These population 3 stars could grow extremely massive before collapsing into black holes. Over billions of years, each generation of stars enriched the interstellar medium with heavier elements. When modern stars form from metal-rich gas, they lose more mass throughout their lifetimes and therefore produce lighter black holes when they die. Not every black hole merger occurs in empty space. If mergers happen in gas-rich environments such as near-active galactic nuclei, they may produce electromagnetic signals. Models predict gamma-ray bursts, brief optical flashes, or radio flares. If such signals are detected simultaneously with gravitational waves, they can precisely locate the merger and reveal the surrounding environment of the black holes. The neutron star merger observed in 2017, 27817 demonstrated the power of this multi-messenger approach when gravitational waves, gamma rays, and optical light all arrived from the same source. Besides laser interferometers like LIGO, there is another way to listen for gravitational waves. Pulsar timing arrays monitor dozens of millisecond pulsars across the galaxy, measuring the timing of their pulses with extraordinary precision. When gravitational waves pass through the Milky Way, they subtly alter these signals in a distinctive pattern. This method is sensitive to waves with extremely long periods, from months to years, and can therefore detect the gravitational wave background produced by thousands of supermassive black hole mergers throughout cosmic history. Between stellar mass black holes and the giants at galactic centers lies a difficult-to-observe gap, intermediate mass black holes. Objects between about 100 and 100,000 solar masses are predicted to exist if smaller black holes merge in hierarchical chains, or if dense star clusters create extremely massive stars through repeated collisions. However, direct observational evidence remains scarce. Many candidates come from ultraluminous X-ray sources, too bright to be explained by stellar black holes, yet not massive enough to be confidently identified as supermassive black holes. Some dwarf galaxies show dynamical signs of black holes with a few thousand solar masses at their centers. In ancient globular clusters, where hundreds of thousands of stars crowd into a small region, simulations suggest that repeated stellar collisions could produce extremely massive stars that later collapse into intermediate mass black holes. Some measurements of stellar velocities near cluster centers also hint at the presence of heavy, invisible objects. However, it remains possible that these signals arise from a cluster of many stellar black holes rather than a single one. What is fascinating is that each observational method reveals a different portion of the black hole population. X-ray binaries mostly reveal black holes formed from the evolution of single massive stars. Gravitational wave detectors, meanwhile, often observe black holes merging within binary systems that may form through entirely different pathways. And it is only by combining all these methods that the full picture of how black holes arise in the universe is gradually coming into view. To find black holes in the universe, astronomers do not rely on a single type of signal. Quasar surveys reveal supermassive black holes devouring gas at enormous rates. shining more brightly than their host galaxies. Meanwhile, tidal disruption events expose otherwise silent black holes that only reveal themselves when an unlucky star wanders too close. When these two kinds of observations are considered together, they create a more complete picture of the black hole population, their masses, spins, environments, and their place in the timeline of the universe. The volume of astronomical data today has grown so large that humans alone can no longer process it all. Machine learning algorithms have begun to act as quiet assistants. Neural networks, trained on the properties of known black holes, now scan vast X-ray and optical catalogs, searching for similar signals. More than once, they have uncovered candidates that astronomers previously overlooked, including unusual binary systems where black holes orbit rare types of companion stars. As modern survey telescopes generate petabytes of data every night, automated discovery has become almost essential for maintaining a complete map of black holes in the universe. The future of this field lies in combining many different kinds of signals. Gravitational waves can precisely measure the masses and spins of black holes as they merge. Electromagnetic radiation reveals their surrounding environments and the circumstances of their formation. In some cases, neutrinos may also carry traces of violent collapse events. When all these detectors record the same event, the resulting picture is far richer than any single observation could provide. Behind every black hole lies a story of collapse, collision, or the violent death of a star. But not all black holes share the same origin. Stellar mass black holes form in ways entirely different from the supermassive giants at the centers of galaxies. Intermediate mass black holes lie in a mysterious middle ground, where current models still leave many unanswered questions. For stellar black holes, the story usually begins with a massive star that has exhausted its nuclear fuel. When the energy that once supported the star against gravity disappears, its core collapses almost instantly. If the core exceeds roughly 20 times the mass of the Sun, the collapse can occur in less than a second. Matter is compressed to extreme densities. The outer layers are blown away in a supernova explosion, and the core continues collapsing beyond the neutron star stage to become a black hole. But sometimes the death of a massive star happens quietly. The binary system VFTS 243 revealed one such case. A black hole formed without any sign of a supernova explosion. The star simply seemed to vanish. According to Irene Tambora of the Niels Bohr Institute, most of the energy released during the collapse escaped in the form of neutrinos rather than light or ejected matter. In these failed supernovae, matter falls inward too quickly for the shock wave to break through the outer layers. Neutrinos carry away most of the gravitational binding energy, while the remaining matter disappears behind the event horizon. From our perspective, the star simply fades from the sky, leaving behind a newly born black hole. Recent simulations suggest that magnetic fields may make the story even more complex. When a rotating star collapses, angular momentum causes its core to spin at extraordinary speeds. Powerful magnetic fields threading through the collapsing matter can generate immense pressure, launching some of the material outward at nearly the speed of light. Under such conditions, not all of the star's matter falls into the forming black hole, and these invisible forces may ultimately determine the final mass of that dark object. In the moment when a massive star collapses, magnetic fields can become the deciding factor in the fate of the black hole that is about to form. If the magnetic field lines are strong enough, they can push part of the star's material outward before it has time to fall through the event horizon. The result is a lighter black hole. These ejected streams of matter also carry away angular momentum, causing the remaining black hole to rotate more slowly. But if the magnetic field is weak, the collapse proceeds almost completely. Most of the material falls straight inward, producing a heavier black hole that retains more of its rotational energy. The relationship between magnetic field strength, black hole mass, and spin is gradually emerging as a model that can be tested through observation. This mechanism may also explain a long-standing mystery in astrophysics. Observational data show a striking gap between the heaviest neutron stars and the lightest black holes, roughly between 3 and 5 times the mass of the Sun. Traditional models of stellar evolution struggle to produce black holes in this range. But if magnetic fields expel some of the matter during collapse, the process could naturally create black holes precisely within this seemingly forbidden mass range. This scenario would also leave observable traces. When particles are accelerated to near the speed of light in the streams of matter launched by magnetic fields, they may produce brief gamma-ray flashes. If astronomers detect such gamma signals appearing at the same time a star disappears without a supernova explosion, it would provide strong evidence that magnetically influenced collapse truly occurs in nature. Meanwhile, recent observations are also changing the way we think about the masses of stellar black holes. The Gaia mission has discovered a striking example, Gaia BH3, a black hole weighing about 33 times the mass of the Sun. This is far larger than the typical stellar black hole in the Milky Way, which averages around 10 solar masses. Even Cygnus X1, the previous record holder, is only about 21 solar masses. Gaia BH3 lies roughly 2,000 light-years away from us in the constellation Aquila. Its companion star carries an important clue. Spectroscopic analysis shows that the star is almost completely lacking in heavy elements. This means the parent star that collapsed to form the black hole was extremely metal-poor. Theoretical models have long predicted that such stars lose less mass during their lifetimes, because atmospheres rich in heavy elements are more easily blown away by radiation. A metal-poor star therefore retains much of its original mass and can produce a larger black hole when it collapses. The observation of Gaia BH3 thus becomes an important experimental confirmation of theoretical predictions that have existed for decades. It also suggests that the first stars in the universe formed from primordial gas containing only hydrogen and helium may have produced extremely massive stellar black holes. These primordial stellar black holes may have served as the original seeds for the supermassive black holes we observe in young galaxies shortly after the Big Bang. But when it comes to supermassive black holes, the story becomes much harder to explain. These objects contain millions or even billions of times the mass of the Sun. Observations show that they already existed when the universe was less than 1 billion years old. According to standard accretion models, even if a stellar black hole formed very early and consumed matter at the maximum possible rate for all that time, it still would not grow large enough to reach such enormous scales. Because of this, astronomers have proposed 2 competing scenarios, each beginning with a different kind of black hole seed, to explain the origins of these cosmic giants. One of the biggest questions about supermassive black holes is, where did they begin? One familiar hypothesis is known as the light seed scenario. In this picture, small black holes formed from the first generation of stars, perhaps only a few hundred to about 1,000 times the mass of the Sun, gradually encountered one another in dense environments through many generations of mergers. They grew step by step until becoming the giants that sit at the centers of galaxies. But this pathway requires time, a great deal of time. Recent observations from the James Webb Space Telescope suggest that extremely massive black holes already existed when the universe was very young. They appear so early that the slow merging process of light seeds seems insufficient to explain them. As a result, another idea has been proposed, the heavy seed scenario. In this scenario, black holes do not need to grow gradually from stellar remnants. Instead, an entire giant cloud of gas could collapse directly into a black hole with a mass of tens of thousands, even hundreds of thousands of suns. This process bypasses the normal pathway of stellar evolution entirely. Rather than fragmenting into countless small stars, the entire gas cloud maintains its structure and collapses as a single entity. However, this requires very special conditions. Normally, when a gas cloud begins to contract under its own gravity, turbulence and cooling processes cause it to fragment into many smaller pieces, each piece forming an individual star. To prevent this fragmentation, the gas must remain hot enough that it cannot cool efficiently, while also avoiding turbulence strong enough to tear the cloud apart. Such rare conditions may have existed in the early universe, when intense ultraviolet radiation from nearby galaxies heated the gas and prevented the formation of molecular hydrogen, a key coolant in star formation. New observations are beginning to test these hypotheses directly. The Chandra X-ray Observatory has studied the galaxy cluster Abell 2744, where the cluster's gravity acts like a cosmic lens, magnifying distant galaxies behind it. Among these, astronomers detected X-ray sources from galaxies that existed only about 450 million years after the Big Bang. Estimates suggest that the black holes there had already reached masses between 10 and 100 million times the mass of the Sun at this extremely early epoch. An even more surprising detail has emerged. Some early quasars appear to contain black holes whose masses are comparable to or even exceed the total stellar mass of their host galaxies. In the present-day universe, supermassive black holes typically account for only about 1/1000th of the stellar mass of their galaxies. But such extreme ratios in the young universe suggest that these black holes may have formed before their host galaxies had time to build most of their stars. The James Webb Space Telescope may even have captured a remarkable example of this process. In data from the Cosmos Web Survey, astronomers discovered a colliding galaxy system shaped like an infinity symbol, which is why they nicknamed it the Infinity Galaxy. Strangely, the system's supermassive black hole does not lie in either galactic core. Instead, it sits in the space between the two colliding cores, where dense, turbulent gas swirls violently. Researchers suggest that the galaxy collision compressed the gas to extremely high densities, creating conditions where a black hole could form directly within that gas. If confirmed by further JWST observations, this unusual structure could become clear evidence for the heavy seed scenario, the direct birth of supermassive black holes from uncontrolled gravitational collapse. Cosmological simulations are telling a similar story. A 2022 study showed that in regions of primordial gas known as primordial halos, where strong cold gas streams continuously flow inward, star formation may be delayed. Turbulence keeps the gas from fragmenting, while the inflowing cold streams continue feeding the collapsing region with fresh material. When gravity finally overwhelms all opposing forces, the entire gas region can collapse into direct black holes with masses of about 31, 0, 0, 0 and 40, 0, 0, 0 solar masses. These advanced simulations suggest that under the right conditions, strong cold gas inflows, highly turbulent environments, and continuous mass accumulation, the universe could naturally create massive black hole seeds. No exotic physics is required. Only rare but realistic circumstances in the early universe. And at the center of this story remains the first generation of stars in the universe, the population 3 stars. They laid the very first foundations for the black hole population we observe today. The original seeds for the giants that now dominate the centers of galaxies. In the earliest eras of the universe, stars were unlike anything we see today. They formed from primordial gas composed only of hydrogen and helium, completely lacking heavy elements. This absence of metals fundamentally changed their evolution. Without heavy elements to help cool the gas or drive strong stellar winds, population 3 stars could continue accreting matter and grow far beyond the size of modern stars, sometimes reaching hundreds or even thousands of times the mass of the Sun before collapsing. When these primordial giants died, they could leave behind massive black hole seeds, intermediate mass black holes. These objects lie between two worlds far larger than stellar black holes, yet still smaller than the supermassive monsters found at galactic centers. with masses ranging from about 100 to 100,000 times that of the Sun. They fill the gap between the two extremes of the black hole universe, yet finding them in nature has proven extremely difficult. Most candidates have been identified through ultraluminous X-ray sources, objects emitting far more energy than typical stellar black holes, yet not massive enough to be confidently classified as supermassive black holes. Some dwarf galaxies also show evidence of stars orbiting invisible objects with masses of a few thousand suns, but in many cases, alternative explanations cannot yet be completely ruled out. In young and densely packed star clusters, however, the story may be different. At the cores of these clusters, stellar densities can be 1,000,000 times greater than in the regions surrounding the Sun. In such crowded environments, massive stars and small black holes do not merely influence one another through gravity, they can actually collide. These repeated collisions can lead to a chain reaction known as runaway collisions. Detailed simulations suggest that within the first 8 million years after a star cluster forms, many main sequence stars may gradually merge into a single giant star weighing about 315 solar masses. Later, a smaller black hole of around 12 solar masses may swallow this star, creating an intermediate mass black hole. And the story does not end there. Roughly 100 million years later, the newly formed black hole may merge with another black hole of about 22 solar masses, growing even larger. Researchers now describe 3 main pathways that could lead to the birth of intermediate mass black holes in such dense environments. The first is the gradual merger of stellar mass black holes through gravitational wave emission. The second involves repeated collisions between massive stars in the cluster core, forming extremely massive stars that later collapse into black holes. And the third pathway is the gradual accretion of stellar material onto existing black holes, allowing them to grow step by step through repeated episodes of feeding. Modern simulations capable of tracking millions of individual stars within globular clusters have finally begun to reproduce this entire process. In these models, extremely massive stars arise naturally and eventually evolve into intermediate mass black holes. Some predictions even suggest that during the evolution of a globular cluster, stars could grow to 10,000 times the mass of the Sun before collapsing, forming black holes of 3,000 to 4,000 solar masses. These predictions still await confirmation from the next generation of telescopes. And when we look up at the night sky from Earth, it is difficult to imagine that these distant objects are directly connected to us. The iron atoms in human blood were once forged in the cores of ancient stars, stars that, in some cases, ended their lives by collapsing into black holes. The calcium in our bones has also passed through many generations of stars before becoming part of living bodies. In this sense, every black hole is a chapter in the long story of cosmic evolution. From small stellar remnants to the giants at the centers of galaxies, each formation pathway reveals how matter, energy, and space-time interact under the most extreme conditions nature can create. The search for intermediate mass black holes is now accelerating rapidly. Next-generation gravitational wave detectors will have the sensitivity needed to detect mergers within this mass range. The LISA mission in space will track binary systems containing intermediate mass black holes across cosmic history. Meanwhile, ground-based detectors such as the Einstein Telescope and Cosmic Explorer will fill the frequency gap between LIGO and LISA, the region where signals from these elusive black holes are expected to appear. At the same time, electromagnetic observations continue to advance. The Event Horizon Telescope network is expanding, promising increasingly detailed images of the regions near event horizons. New X-ray telescopes will help distinguish the accretion signatures of intermediate mass black holes from other ultraluminous X-ray sources, and sometimes a simple but violent sign may reveal their existence. When a wandering star passes too close to an intermediate mass black hole, immense tidal forces tear it apart. The falling debris produces a brilliant flare, a signal that can be observed across enormous cosmic distances. A brief flash of light in the darkness, marking the place where a hidden black hole lies. When a star is torn apart by the tidal forces of a black hole, the light it produces is not just a simple flare. Its light curve, along with the signatures in its spectrum, changes very sensitively, depending on the mass of the black hole responsible for the event. These subtle details allow astronomers to distinguish between stellar black holes, supermassive black holes, and the elusive objects in between intermediate mass black holes. A few tidal disruption events have already revealed hints of them in places no one expected. Meanwhile, increasingly detailed simulations are deepening. Another mystery, the role of magnetic fields in the deaths of massive stars. Recent studies suggest that magnetic field lines threading through collapsing matter may determine not only the spin of a newly formed black hole, but also its final mass. This is particularly important for a long-standing gap in observational data, the mass range between roughly 3 and 5 times the mass of the Sun, lying between the heaviest neutron stars and the lightest black holes. Classical stellar evolution models struggle to produce black holes in this range, but when magnetic fields influence the collapse, matter can be expelled in ways that allow black holes to form precisely within this seemingly forbidden region. These magnetic processes may not only shape the black hole but also produce some of the most brilliant signals in the universe. Gamma-ray bursts, the brightest explosions ever recorded, may originate from energy concentrated and released by magnetic fields in the moment a black hole is born. It has long been known that long gamma-ray bursts are associated with the deaths of massive stars. Yet, the exact relationship between the characteristics of the explosion and the black hole left behind remains uncertain. If the strength of magnetic fields during collapse determines both the energy of the explosion and the spin of the resulting black hole, then the light from gamma-ray bursts could serve as a clue to infer the properties of black holes that we may never observe directly. While physicists continue to investigate these processes, new observations from the James Webb Space Telescope have introduced another challenge. Enormous black holes have been discovered when the universe was only about 500 million years old. They are so massive that conventional growth models struggle to explain them. This forces theorists to consider two possibilities: either black holes can grow much faster than current physics predicts, or their initial seeds were far larger than the remnants of stars. One potential solution is the direct collapse scenario. In this model, giant clouds of gas do not fragment into stars, but instead collapse as a single body to form a massive black hole from the beginning. For this to happen, however, the gas must remain primordial, free of heavy elements that would cool it and cause fragmentation into many smaller stars. Such conditions may have existed in the early universe, particularly in rare regions where strong radiation from nearby star-forming areas suppressed the formation of molecular hydrogen and kept the gas hot. Cosmological simulations are still trying to determine how rare such environments were. If they were common, direct collapse might explain a large fraction of supermassive black holes. If they were rare, it may represent only an unusual pathway. Another, even more radical idea is that of primordial black holes. According to this hypothesis, black holes did not require stars or galaxies to form. Instead, they could have arisen directly from tiny density fluctuations in the first moments after the Big Bang, when energy variations in the early universe were strong enough to create regions that collapsed gravitationally. Such black holes could span a vast range of masses, from extremely small objects to thousands of solar masses. So far, there is no definitive evidence for them, but they remain an intriguing candidate for dark matter and possibly even the first seeds of supermassive black holes. In the future, gravitational wave detectors may help test this hypothesis. If they detect mergers of black holes with mass distributions that cannot be produced by ordinary stellar evolution, that could indicate a primordial origin. Amid all these hypotheses, one recent discovery has drawn particular attention: the Infinity Galaxy. In this colliding galaxy system, a supermassive black hole appears to lie between the two galactic cores, surrounded by a sea of turbulent gas. The collision has compressed the gas to extremely high densities, while gravitational forces and continuous inflows of matter funnel gas toward the center faster than star formation can consume it. In such a chaotic environment, a cloud of gas could accumulate hundreds of thousands, even millions of solar masses before collapsing into a black hole in a single moment. Future observations will test whether this scenario is correct. If it is, the gas surrounding the black hole should show primordial chemical signatures, unpolluted by material that has passed through stars, and the mass of the black hole should correlate closely with the total mass of gas involved in the collision, rather than with the stellar mass of either of the original galaxies. Such clues could confirm that, under the most extreme conditions, the universe is capable of creating enormous black holes in a single gravitational collapse. If a supermassive black hole truly forms from the direct collapse of gas after two galaxies collide, its formation time should reflect that collision itself. It would appear very quickly, within only a few tens of millions of years after the two galaxies begin to merge, rather than growing gradually over billions of years by accreting gas and merging with smaller black holes. However, to understand the deeper origins of the first black holes, astronomers must look back to a time we have never directly observed: the population 3 stars, the first generation of stars in the universe. So far exist only in theory. They formed within the first few 100 million years after the Big Bang and disappeared long before humanity had the ability to observe them. Yet, although the stars themselves are long gone, their remnants may still exist, perhaps in the form of intermediate mass black holes hidden within ancient globular clusters or distant dwarf galaxies. The James Webb Space Telescope may provide the first opportunity to see these stars during their formation. Ultraviolet light from population 3 stars at extreme distances would be stretched by the expansion of the universe into infrared wavelengths, exactly the range JWST was designed to observe. Even if we cannot see them directly, their traces may still be discovered in another way, through cosmic chemical archaeology. When population 3 stars exploded as supernovae, they enriched interstellar gas with elements forged in their cores. Stars that later formed from this gas would carry a distinctive chemical signature in their atmospheres. Some extremely metal-poor stars have already been discovered, whose elemental patterns suggest they may have formed from material produced by a single population 3 star. As spectroscopic surveys expand, statistical analysis of these chemical fingerprints may reveal the masses of the first stars, how they died, and how efficiently they produced black holes. Meanwhile, an entirely new tool has transformed how we study black holes. In less than a decade, gravitational wave astronomy has turned theoretical predictions into direct observations. In 2015, the first signal from 2 merging black holes was detected, confirming that such collisions could generate ripples in space-time strong enough to travel across billions of light-years and still be measured on Earth. Since then, dozens of additional mergers have been recorded, revealing a black hole population far more diverse than initially imagined. Their mass distribution, spin rates, and merger frequencies continue to force revisions of theoretical models. One of the biggest surprises lies in the masses of these black holes. Some fall within the previously forbidden region between neutron stars and the lightest black holes predicted by stellar evolution. Others are far more massive than any single star could produce, suggesting they grew through repeated mergers. Spin measurements have revealed similar surprises. In many cases, black holes appear to rotate faster than predicted, indicating either that their parent stars retained more angular momentum than expected, or that the black holes themselves experienced earlier merger events that increased their spin. Future observations will extend this story into a different mass range. Mergers involving intermediate mass black holes produce gravitational waves with lower frequencies than those generated by stellar black hole mergers, meaning they require space-based detectors like LISA to be observed effectively. When LISA launches in the 2030s, it will open an entirely new observational window into the population of intermediate mass black holes, potentially detecting hundreds of mergers each year and finally revealing whether these long-sought missing links exist in the numbers predicted by theory. At the same time, observations increasingly reveal a deep connection between black holes and galaxy evolution. Supermassive black holes do not simply sit quietly at galactic centers. They can launch enormous flows of matter and energy, heating or expelling gas from galaxies, the very fuel needed for star formation. This feedback mechanism explains why black hole mass is so closely correlated with the mass and structure of the host galaxy. Modern simulations now track this coevolution over billions of years. Initially, black holes grow rapidly by accreting gas during phases when galaxies are rich in material or during galaxy mergers. Eventually, the system reaches a delicate balance in which feedback energy from the black hole regulates further accretion, allowing its mass to grow in step with the stellar mass of the galaxy. Sometimes, a galaxy that once seemed stable suddenly awakens, a galactic merger, or a stream of cold gas flowing in from intergalactic space can supply fresh material to the central black hole. When that happens, the black hole enters a phase of violent growth. Such galaxies shine brightly as quasars, while others, where the fuel has been exhausted, leave behind quiet black holes, detectable only through the motions of the stars around them. On the scale of galaxies, these processes resemble a vast cosmic climate system. Supernovae heat the gas in star-forming regions. Winds, driven by supermassive black holes, spread throughout the galaxy, pushing and heating surrounding matter. Meanwhile, streams of cold gas from outside space continuously replenish the supply of raw material. The delicate balance between these processes determines the fate of a galaxy, whether it continues forming stars and glowing with the blue color of youth, or gradually cools and turns red as its stellar population ages. Many massive galaxies in the universe today have reached that latter stage. The black holes at their centers have grown large enough to inject powerful feedback energy into their surroundings, preventing gas from cooling and forming new generations of stars. But the origins of black holes may reach even deeper than stars themselves. One bold hypothesis suggests that some black holes formed in the very first moments after the Big Bang. These primordial black holes would not require collapsing stars or gas clouds. Instead, they could arise from tiny quantum fluctuations in the energy density of the early universe. When slightly denser regions collapsed under their own gravity, depending on the timing and local conditions, their masses could range from extremely small objects to thousands of solar masses. If they exist in large numbers, such objects might even contribute to dark matter, the invisible component that makes up most of the mass of galaxies. However, many observational tests have begun to place limits on this idea. Microlensing surveys search for stellar mass black holes passing in front of distant stars. Gravitational wave detectors look for the characteristic mergers they would produce, and observations of the cosmic microwave background test how such objects might have influenced the evolution of the early universe. So far, the results suggest that primordial black holes are unlikely to account for all dark matter. Even so, every new observational advance raises additional questions. How many black holes are created through failed supernovae? How important are magnetic fields in the deaths of massive stars? Through what mechanism did the first seeds of supermassive black holes appear? And how many intermediate mass black holes remain hidden in ancient star clusters that we have not yet detected? Every black hole in the universe is the result of a different pathway. Some are born from the silent collapse of a star. Others emerge from the violent explosion of a supernova. Some arise from stellar collisions within dense clusters. and others may form from the direct collapse of an entire giant cloud of gas. These different pathways connect the scales of the universe from the smallest quantum processes to the largest cosmic structures. To understand how black holes form is also to understand how matter transforms under extreme conditions, and how gravity shapes reality itself. This story is far from finished. Observers continue to peer deeper into space and time, while theorists push simulations to new limits. The universe is still creating black holes through all these pathways, some in regions close to our own galaxy, others so distant that only faint signals from the dawn of the universe reach us. And somewhere out there, right now, a massive star is entering its final seconds. Its core is collapsing at nearly a quarter of the speed of light. Matter is being compressed to densities that modern physics still struggles to fully understand. A new black hole is about to be born. A massive star can transform into a black hole with almost unimaginable speed, in less time than it takes to finish reading a single sentence. Its core collapses, and a new black hole is born, a permanent tear in the fabric of space-time. Humans do not witness that moment directly, but we are observing its traces throughout the universe. Gravitational wave detectors listen for the ripples produced when two black holes merge. X-ray telescopes capture the final light emitted by matter just before it disappears beyond the event horizon. Networks of radio telescopes image jets of material launched at nearly the speed of light from active black hole systems. Each of these observations adds another detail to the picture of how black holes form a picture that is still incomplete. One of the biggest missing pieces involves magnetic fields. Simulations suggest that the strength of magnetic fields during a star's collapse may determine both the mass and the spin of the newborn black hole. If this is true, black hole masses and spins should follow a clear pattern. But confirming this hypothesis requires more data, more black hole mergers with precise spin measurements, and more gamma-ray bursts that can be directly linked to the birth of black holes. Meanwhile, intermediate mass black holes continue to evade detection. Theory strongly suggests they must exist to bridge the gap between stellar black holes and the supermassive giants. Simulations show they could form naturally in dense star clusters where repeated stellar collisions occur, yet observational evidence remains scarce. The future LISA mission may change this by detecting mergers in the mass range that current detectors can barely observe. The question of supermassive black hole seeds runs even deeper. It is possible that they do not originate from a single mechanism. Observations such as the Infinity Galaxy suggest that direct collapse of gas may occur during galaxy collisions. The remnants of population 3 stars may have produced heavy black hole seeds early in cosmic history. And in an even more radical possibility, primordial black holes may have formed from quantum fluctuations in the early universe. All 3 pathways could coexist, each leaving distinct signatures that astronomers are still trying to identify. The James Webb Space Telescope continues to push the boundaries of what we thought possible. Again and again, it finds black holes that are either too massive or appear too early, compared with theoretical predictions. Objects that should not yet exist, yet clearly do. Masses that standard growth models struggle to explain. And chemical signatures suggesting formation from primordial gas. This forces theory to evolve, opening the door to new mechanisms, explaining how black holes can grow rapidly or form from massive seeds. In reality, the universe has never stopped producing black holes. Failed supernovae quietly transform stars into black holes without any visible explosion. Magnetic fields continue shaping their properties during stellar collapse. Globular clusters remain natural laboratories where stellar collisions may produce intermediate mass black holes. And in the most distant regions, rare clouds of gas may still be collapsing directly into massive black hole seeds. Never before have we come so close to understanding the origins of black holes. Gravitational waves have revealed populations of black holes we never knew existed. Images of black hole shadows have confirmed bold predictions of general relativity. Chemical archaeology traces the origins of ancient stellar remnants, and computer simulations are beginning to reproduce the mass distributions and merger rates we observe. The pieces are gradually falling into place, but many mysteries remain. Why are the masses of black holes and galaxies so closely linked? How exactly does black hole feedback regulate star formation? What truly happens at the event horizon when a black hole is born? And does information really disappear when it falls into a black hole? Or does quantum mechanics preserve it in some hidden way? These questions belong not only to astronomy, they touch the deepest problems in physics, where the nature of space-time and information itself is tested. The next decade may bring answers. Detectors such as the Einstein telescope and Cosmic Explorer will observe thousands of black hole mergers each year. With that data, scientists may finally be able to distinguish the different pathways of black hole formation and understand how these mysterious objects came to exist in our universe. In the coming decades, humanity will observe the birth of black holes in ways never before possible. The LISA mission will follow the growth of supermassive black holes across billions of years of cosmic history. Next-generation X-ray telescopes may capture the moment a star collapses, when matter first disappears beyond the event horizon. And if a collapse occurs close enough, neutrino detectors could record the signals escaping during the final seconds before the black hole truly forms. Each pathway that creates a black hole carries a different story. Some massive stars, once brilliant nuclear furnaces, ultimately collapse into gravitational prisons. In dense star clusters, repeated collisions can build intermediate mass black holes through chains of violent mergers. In rare regions of the early universe, giant clouds of gas may collapse directly into massive seeds without any stars as intermediaries. Some failed supernovae cause a star to vanish almost silently, while in other cases powerful magnetic fields shape the mass and spin of the black hole in the final moments of collapse. The remnants of population 3 stars may have planted the first seeds for supermassive black holes that appeared billions of years later. And in even more radical scenarios, primordial black holes may have formed from tiny fluctuations in the young universe itself. But black holes are not merely strange objects of astronomy. They are silent architects of the cosmos. Through powerful flows of matter and energy, they regulate the evolution of galaxies. Their jets and winds stir surrounding material and disperse heavy elements forged in earlier generations of stars. And in the extreme environments around them, the laws of physics are tested at limits that laboratories on Earth can never reproduce. In a sense, this story is connected directly to us. The atoms in the human body once passed through ancient stellar life cycles. The iron in our blood was forged in the cores of stars before those stars collapsed. The calcium in our bones was thrown into space when massive stars ended their lives. The matter that makes us is the residue of violent cosmic events, many of which ultimately led to the birth of black holes. Right now, somewhere beyond our sight, these processes are still unfolding. A star is collapsing. A cloud of gas is shrinking into a massive seed. Stellar mass black holes are merging to form larger objects. And the supermassive black holes at galactic centers continue to grow from seeds formed when the universe was young. The universe has never stopped creating black holes, and there may still be formation pathways we have never even imagined. The history of science shows that every advance comes with surprises, observations that defy expectations, and force scientists to rewrite their theories. What we know for certain is that black holes can form in many different ways. Each pathway leaves its own signature: the mass of the black hole, its spin, the orbital configuration of binary systems, or the chemical composition of the surrounding environment. These signals reach us in many forms: gravitational waves from mergers, X-rays from accreting matter, gamma-ray bursts from dying stars, and neutrino pulses from collapsing stellar cores. Each piece of data is like a surviving record of an event that occurred billions of years ago, Astronomers are learning how to read these records, reconstructing the story of the birth of each black hole. That process is still ongoing. Black holes are not merely relics of the distant past. They are still being born, still merging, still reshaping the structure of the universe. Some may slowly evaporate through Hawking radiation in the far future. Others will continue merging, becoming ever larger as galaxies collide. The question of how black holes form connects nearly every field of astronomy. Stellar evolution determines which stars end their lives as black holes. Their chemical composition determines how much mass they lose during their lifetimes. Dense environments allow collisions that would never occur in emptier regions of space. And the special conditions of the early universe open the possibility of direct collapse of gas into massive seeds. This story is still being written. Every new discovery, every new signal from deep space, brings another clue about how these mysterious architects of the universe are born. And somewhere, a scientist is waiting for the next signal, a ripple in space-time, a flash of X-rays, or a faint pulse of neutrinos carrying the secret of the birth of another black hole.